So the next speaker is going to be Denis Kochan, and the title of his talk is Graphene Spin Relaxation, the Roles of Adatom in Magnetic Moments.
Yeah, thank you very much for kind introduction. Can you hear me? Great. So thanks organizers for inviting me and giving me opportunity to talk here. So today I was expecting that the audience maybe will be a little bit mixed with people doing Raman spectroscopy and optics, so I prepare a little bit talk which should be colloquial. And since I'm talking about the relaxation, I'm also a little bit relaxed dress, but there will be also tight binding, so you can complain that I should be more tight, but okay. So let me start. So Paolo already introduced you where is the Regensburg. Regensburg is the east-south part of the Bavaria, and the most important thing is the Bavarian flag, which was maybe not shown, so that's the main point of the slide. And he also showed you about the two dominantas of the Regensburg, that there is a very old bridge, stone bridge, and there is very famous an old cathedral. But let me tell two other things. So in this cathedral, there is the largest free hanging organ in the world. And there are very nice organ concerts. So everyone who visits Regensburg, there is a fan of the organ music, I am recommending to go and buy tickets. They are very cheap. And the other thing is that the name of the Regensburg is related with a river, and namely also with the fortress, which was called the Castra Regina. And there was a place when Roman soldiers were living, or basically it was the camp of them, and they were protecting the Danube border, because the barbars, Germans, were coming and were affecting Roman Empire. And the last but not least, the most important thing in Bavaria is plotted here. But after visiting the Brazilian restaurant, I also should say that you have a very nice meat. So let me go. This is the outline of my talk. So firstly, some propaganda, just some motivation. And I wanted to mainly tell today something about the spin-orbit coupling and about some model Hamiltonians which allow us to describe the graphene, which is functionalized by adatoms. And then I will go to the spin relaxation, and I want to compare the spin-orbit coupling with local magnetic moments. And I want to convince you that the local magnetic moments are the one who are responsible for the spin relaxation. And at the end, also a few words about the graphene and TMDs, because there were also many TMDs. So I can wait for taking photo, nice photo. Okay, so let me start with graphene. So basically the story is old and well known. So basically there was a Nobel Prize for, let's say, discovering or extrapolating a graphene. And graphene has many wonderful properties. A few of them I was summarizing here. But the thing which basically we would like to have is a tunable band gap. Then would help us to make more electronic-like applications. And the one way how to do it was that maybe functionalized graphene can help with that. Okay, so that was the first thing. And the second thing is the graphene spintronics. And graphene spintronics is quite wide object or subject. So basically spin can be affected by many ways. So for example, you can have a substrate which can affect the spin, or ferromagnetic electrodes, or basically some things you are putting on to cover it, or there could be the adatoms. So many things will affect the spin dynamics, and the main features which we are then interested in spintronics is like a strand of the spin orbit coupling, spin relaxation, quantum physics, magnetism, and things like that. So spins then enters many other areas which could be interesting theoretically or also for some, let's say, technological applications. Okay, so this is the end of the propaganda. So I am showing a nice paper where there are many summary things about the graphene spintronics by Jaro and Martin. So Jaro is my boss, Martin was my colleague, and there is also the PIs which are contributing to the graphene flagship. So they also made some European flagship perspective, how they see the potential evolution, or what are the possible application of graphene spintronics. So you can go for more details there. Okay, so let me start with the spin-orbit coupling. So Martin already did something today, but I will do it in my way, in my unique way. So basically, let me start with the carbon atom. So if you are starting with the carbon atom, that what you are seeing schematically here are the atomic shells. And basically what is important are the valence shells, which is a 2p electrons, and if you are doing some excitation, also a 3d electron. And if you are looking in the spectroscopic data and you are looking for fine structure splitting of those things, you are seeing that P level is splitted by roughly 10 MeV and the D level by 0.3 MeV. And basically, this splitting is nicely visualized by this cartoon that effective electric field, which is produced by the nucleus, is in the reference frame of the electron, transformed as a magnetic field, and effectively magnetic interaction and spin interaction basically do the spin processes. So this is, let's say, the children Wikipedia definition. What is the spin-orbit coupling? Okay, if you put the graphene on the lattice, you are modifying such nice structure because you are getting sp2 hybridized guys, and then you are getting a pz electrons, which are basically perpendicular to the level, and they are having a very nice and famous linear dispersion. So if you look closer in that, so this is the electronic band structure. So those pi electron bands, which are lying close to the Fermi level, are very nicely separated from this S or sigma levels. Basically, the difference is roughly 3 electron volts. And if you are now asking where is the spin orbit hidden, so we are expecting that the spin orbit from single atom should be roughly 10 MeV. We would naively say 10 MeV should be somewhere hidden here. So let's look where it is. So if you are looking for the splitting of the pi bands, you are seeing that the spin orbit coupling is very small. It's about 50 microelectron volts according to the latest calculation and measurements. But in 2009, the Martin calculation showed that it's 24 micro, which is very close to the value which is nowadays believed to be true. But if you're seeing that the most of the contributions, almost 9 electron volts, is hidden in the sigma bands. And so basically we see that spin orbit coupling is here, and now there would be the nice thing. So we are seeing that the spin orbit coupling around the Fermi level is very weak. However, in the sigma bands, it's quite large. So there is a natural idea. Are we able to transfer part of that to here? And the answer is that yes. And okay, so that I said that spin orbit coupling is weak, and the answer or the things we would like to do is what I described below, but still let me continue in terms of the models. So here is the evolution of the spin orbit coupling gap as a function of the transverse electric field. So transverse electric field, it means that it is perpendicular to the graphene sheet, and this basically resembles the substrate. So this, what I was showing before, is for the freestanding graphene. But if you will include the substrate, you are effectively breaking the mirror symmetry in this plane of the graphene. And what happens is that the spin orbit start to play a role, and there will be the splitting. And here you are seeing the splitting of the pz bands due to the induced spin orbit coupling due to presence of the electric field or of the substrate, or very nicely seen in this picture. And the two main Hamiltonians which people use if they are describing the spin orbit coupling in graphene are those two things. So this is something what is traditionally called the intrinsic spin orbit coupling, and Martin was telling us about that. So tau is something which tells you whether you are in the K prime or K point. SZ is something which tells you that whether you are spin up or spin down, and sigma Z is telling you whether you are on the sublattice A or sublattice B, because the unit cell of the graphene has 2 atoms. So basically, this Hamiltonian is 4×4. And this is the effect which is responsible for this picture or this dynamics of the bands, and it's conventionally called as a Rashba. And in the case of the graphene, which is put on the substrate, this is the conventional form of that. Okay, so we can say, fantastic. Spin orbit coupling is very weak. We can use graphene as a perfect platform for spin logic manipulations. Yeah? So we are creating something, and then we can move the spin because spin will not relax fast because the spin orbit is weak. So fantastic, we can do the spintronics. But as I will show you the experimental data, the spin relaxation is very fast. So basically this would not work because spin would relax in roughly 100 picoseconds or 10 picosecond time scale. So this would not be enough, or this would not be able. But never mind, if you would have a very strong spin orbit coupling, we still can have a very nice spintronic applications. As proposed in this seminal paper by Kane and Melle, basically we can have a quantum spin Hall effect. So basically spin will basically propagate due to the strong spin orbit coupling on the edges, and basically you can get a pure spin current on one edge or the other one, depending how you will gate it, etc. And this is a nice basically view which then opened the full plethora or basically the full area of this topological insulators. So this I wanted to show that there is some non-trivial topology like that. Okay, so as I said, there are two ways how to functionalize graphene from the point of view of spin orbit coupling. So the first one is, as I will show you, to put some adatoms on top of it. And in that case, we will create some local random spin orbit coupling environment. And in other cases, to put graphene on something which is strong spin orbit active, let's say TMDC. And this I will maybe tell something about that at the end. Two mainly differences is that this is a local and very random in a sense. But if you are able to, let's say, in the organized way, put the adatoms, then you can make it less random. However, here it is more uniform, and it's a proximity-like spin-orbit coupling. And what we will see, and at least our studies show us, that the spin orbit is rising for the pi electrons from roughly 10 microelectron volts to roughly 110 or 50 MeV. So this is a dramatical enhancement of that. Okay, so let me start with the adatoms. And I think the first idea was pursued by Antonio Castronetto and Paco Guinea. And the basic idea which they have is basically provided here. So what we wanted is, as I was saying, we want to transfer part of the spin-orbit coupling, which is hidden in the sigma bands, to the spin-orbit coupling, which is on the Fermi level, which means on the pi bands. And the way how you can do it is that you will do p-sigma mixing by, let's say, adatoms can deform the lattice, so they will create this apex. And in this apex, the pz electrons will mix with px and py electrons, and basically those are spin-active. So this is the first thing how it can come. So there is a geometrical deformation which will allow p-sigma mixing. That's the one thing. But imagine you will put here something heavy, let's say copper or fluorine. Then this guy itself has its intra-atomic spin-orbit coupling, and this intra-atomic coupling can also leak to the graphene, and basically you can get intra-atomic contributions. Yeah, so intra-atomic contribution is then donated to the graphene. So basically there are two channels how you can do it, and we basically were studying that. So let me describe the strategy, since I want to be, say, pedagogical or let's say colloquial more. So the strategy which we were doing, I would say we are not more continuing in this business, but it was always like that. So at the beginning there was some DFT calculations, so pioneering with Martin and then his descendant Toby and Klaus Zollner. So basically, and the story was something saying, so they take some, so you will see, some supercell, some adatom, and they computed something. Then there were some data, and then we wanted to make some effective spin-orbit coupling Hamiltonian and fit it to those data. And at the end, if we had this spin-orbit coupling Hamiltonian, we want to do some transport studies and to see whether it's useful for that. So basically, I was working with Toby and behind that is the chief executive officer who is basically supporting us, and he is also responsible for money and conferences that we can go. Okay, so this is the basic strategy, let's say, how it was organized in persons. And now let's come how it looked on one particular example. So what you are seeing on this graph is the electronic band structure for the hydrogen atom, which is sitting on top of the graphene. That was like 5 by 5 supercell. And what you are seeing, there are 3 bands which are close to the Fermi energy. So basically those 3 guys we are interested in. And then we are also knowing how many or how much and what kind of orbitals are contributing to which bands. And basically what we are seeing that it's mainly pz orbitals or s orbital from that. So the basic idea or basic model how you can on the orbital level simulate the hydrogen chemisorption to graphene is this simple Anderson-like model that you are having a hydrogen level. This hydrogen level is somehow shifted by energy epsilon compared to carbon levels. And then there is a hybridization between the hydrogen orbitals and the host carbon atom. So basically this was the simplest model. We take it, we fit the numbers, and basically you are seeing the fits around the Fermi energy. So basically just 2 parameters are perfectly fitting this thing. So let's say this is the first simple part. The second thing is that from the DFT you also know what is the splitting of those 3 bands. Yeah? So this is the splitting of the conduction band. This is the splitting of this impurity or mid-gap band. And this is the splitting of the conduction band. And the idea is to describe that. Okay, and we developed some methodology. I will slightly just show you how it works. And basically we are having the Hamiltonians which are expressed in this one-year basis or in the local basis if you wish. So there are normally 3 terms. I will shortly describe each of them. Conventionally, or let's say on the historical reasons, we call this intrinsic. However, it's not true intrinsic, but if you look for this form of the Hamiltonian, it has the form of the Hamiltonian of the Kane and Melle, and they call it intrinsic, so we use the same thing. This also resembles the Rashba term, so we call it Rashba, and there was something new which Martin attributed to Bjorn and others, but we were one of the first who derived it, so just to correct him. Okay, just as for fun, many other people also derive it. So the first term is conventional, so basically this is the position of the carbon atom, this is the position of the adatom, and this intrinsic spin-orbit coupling is in the nature next nearest neighbor one and preserves the spin. So this is the something which causes spin-preserving hopping, but it is a spin-orbit coupling term. So it's not an orbital thing. So spin down and spin up differ in the sign if they're hopping. The second term is what I said is called the Rashba, and this is the nearest neighbor coupling between three nearest neighbors and the host carbon atom. And this thing is the spin flipping term, and it's a nearest neighbor one. And the one which we are calling a PIA, which is like a pseudo-spin inversion asymmetry, this is the next nearest neighbor coupling, which couples the next nearest neighbors around the impurity. And this one is somehow the mixture of those two. In one case, it is a next nearest neighbor hopping, but on the other side, it is the spin flipping. So this term you don't have in the plain graphene. Only if you break some certain symmetries, then it will appear as Marcin showed us. Okay, so this is basically this term. Okay, so what we did, we take this simple Hamiltonian. I will also slightly show you how to derive it. And basically, we were fitting it, and basically there are these free fitting parameters. And if you are seeing roughly the strength of the spin orbit coupling due to the hydrogen is roughly 1 MeV. Yeah, so from 10 microelectron volts, we are going to 1 MeV. And we can attribute those numbers that this is purely geometrical effect because the hydrogen atom is so light that it cannot donate any intrinsic spin orbit coupling to the graphene. So this is the purely, let's say, geometrical or apex contribution, as you wish, yeah? And okay, we are deviating a little bit here, but okay, so main fits are in those gray zones, and those gray zones are very close to the, or basically this is in this region around the K point. If you go far away, then also there is contribution of other orbitals, yeah, and those orbitals were not included in this simple effective tight binding. But if we will make the extended model, I believe we can perfectly fit those lines. But okay, so we are thinking that the Fermi energy can be changed in this energy window, and I would say for that, the effective model is very nice. Okay, so how we do it? So there was extended lectures about the group theory. I want to show it that one can approach this from completely opposite corner, that no representation, decomposing, but exactly opposite. So we will create the Hamiltonian knowing how your orbitals are transporting. So what we know that for those adatoms which considered the main dominant orbital is either S for hydrogen, PZ, it was the dominant for fluorine, or DZ square, this was the important for the copper adatom. And then the structure locally, if you are looking, it looks like it is a C3V symmetric structure. If there is not any electromagnetic field, then we are also having a time reversal symmetry. And what we are just looking is, we are just looking what terms are allowed around the impurity, which are nearest neighbor or next nearest neighbor. You can play this game to next nearest neighbor if you wish, but basically, since the spin orbit couplings should be somehow assumed to be large only around the impurity, we just constrain ourselves to the nearest and next nearest neighbors. Okay, then, okay, you can look for the character table, but basically this is useless now. What is important is just to start to work. So I have a PZ orbital, which is sitting on the position B1. So it's something which is pointing up. And assume there is an electron which has a spin up. And now I am asking, is it possible that such electron due to spin orbit coupling will jump on this atom A and will preserve its spin up? And now I say, if this coupling is allowed, then all symmetry combination which I will do should give me the same number. So for example, I am able to express this orbital as a mirror reflection of that orbital. So this is my mirror reflection plane is pointing here, so it's plotted here. So spin down electron, if I will mirror, then it will produce me spin up electron, a part of some correcting factors. So if this is symmetry, then those two things should be equal. This is the unitary transformation. So basically, I can calculate out. E and E are getting out and producing just factor 1. So basically, what I am seeing is that if this is allowed, the same value should be assigned to such spin orbit coupling hopping. But if you are now using things that this is the most general form of the Hamiltonian, this is some orbital operator. It's not necessarily angular momentum, but you don't need it. What is important is sigma z, and you are saying that this should be exactly minus of that. So you are saying that this is equal to that. So you know that there is not allowed the nearest neighbor spin conserving hopping. And by doing this, basically you are able to discover what are the allowed couplings. Okay, so this is the simplest ways I want to show, and basically this is the concluding the story. So this is the orbital part, this is the spin orbit part, which I was trying to show you how we did it. We also played a little bit with the magnetism, because later you will see that some adatoms are bringing also the magnetic moment to the game. So we were also considering that there can be induced magnetic moment on the impurity sign, and then the conduction electron can jump on the impurity, do some spin rotation there, jump and go away. And basically this is the main summary of the adatoms we were doing. So it was hydrogen, fluorine, methyl, copper. Here you are seeing the preferential position, whether they want to sit on the top or in the breech, because this is also allowed. Here we analyze the question of the magnetism, and we clearly say that hydrogen, methyl, and copper, they are bringing magnetic moment to the game. And then we also analyze the resonances, you will see a little bit later. And here you are seeing the strength of the spin-orbit coupling. So for the hydrogen and methyl, you are seeing that the largest spin-orbit coupling is about 1 MeV. And as I was telling you, 1 MeV is basically the value which you will get from this distortion. So this is purely geometrical effect. But in the case of the fluorine and copper, you see that the induced spin-orbit coupling is 10 times larger, and here it's 50 times larger. So we interpreted that this is the donation from the intraatomic spin-orbit coupling from those guys to the graphene. So this is the main mechanism about the effective spin-orbit coupling. And then later I will show you how to use this Hamiltonian and compute something useful from that. Or at least I believe it's useful. Okay, so let me now move on and say something about the spin relaxation in graphene and about the challenge to explain it. And the challenge is as follows. So if we are looking for the spin relaxation in the single or in the bilayer graphene, then basically you are seeing this data. So those data are for the single layer graphene, and those data are for the bilayer graphene. There are many experiments. I am just showing the data from the group of Roland Kawakami. And what you are seeing is the spin relaxation rate in the inverse of the seconds as a function of the gate voltage, which basically is the things which change your Fermi energy. And the same is plotted for the bilayer graphene. And if you are looking in those two figures, you are seeing immediately two things. The first of all, you are seeing that there is a qualitative difference. So here we are having a hype. However, here we are having some valley or shoulder or something like that. This is the first thing. And the other thing is, if you are looking for the magnitudes, the spin relaxation is really ultra fast. So we are talking about here 100 of picoseconds or 10 of picoseconds in both cases. So we are really having the ultra fast spin relaxation, which cannot be explained due to the small or this weak spin orbit coupling, which I show you, and also Martin showed you that the B square is quite small for the graphene. Okay, so how to do the spin relaxation, or what is the spin relaxation? So basic thing is that you are injecting somewhere the electron, I don't know, and it's doing some random motion, and it interacts with the impurities, phonons, magnetic impurities, and at some point it changed the spin, and the characteristic difference or space difference along which this happens is called the spin flip path, and this is the spin relaxation time. Okay, so this is the cartoon-like of that. And okay, so how the people are doing in the experiments. So basically, these I have from some presentation of people from Bart van West group. So basically take the graphene, and they are making a sample, and the guy is explaining how. So take the graphene, take the Scotch tape, put it, extrapolate it, put it on the silicon substrate, repeat it several times, and then you are getting a flake. Then you are taking this flake, and you need to put on the electrodes, and there are the electrons in which you are injecting the spin current, and then there are the electrons at which you are measuring or detecting the spin signal. Yeah, so basically all these measurements are done indirectly, in a sense that it's kind of the transport measurements out of which you extract the spin relaxation. It's not something that you are shining a light and you are doing some, let's say, spin spectroscopy or something like that. Okay, so this is the situation. So here, let's say, you are injecting spin down electrodes. Here you are extracting spin down electrodes. So basically the spin profile in this region looks like that. And then you are looking how it's diffusely propagated, and you are seeing, so this is the space-like figure of the spin profile of spin up and spin down electrons, and then on those electrons you are measuring difference in those signals, and out of that you are getting some non-local resistance, and then the experimentalists are changing the magnetization of those electrodes, so they are now injecting and extracting different spins, so basically spin profile looks differently, and playing with that, they are able to basically measure this non-local signal as the difference of those two voltages, and they are getting something out of that. And there is a nice theory which enables you from those jumps tell you how strong is the spin orbit coupling. So this is the one way how it is done. It's called the spin valve measurements. And the other one is the Hanle. Martin was telling about that. So basically you inject the spins, you apply magnetic field, spin somehow effectively presses around this magnetic field, and then depending on the magnetization, you can have larger or smaller electric signal, because spin up, let's say, can enter here and spin down cannot. And this is the way how it was measured. So I am not experimentalist. Let me tell you how to compute things like that. And here I try to prepare a joke, but you will tell me whether it was good or not. So you can do it like that how to calculate it. And the thing is that you can do some serious calculation. And serious calculation is if you are having a serious politician. And the other thing is that you can make some more naive calculations, and it's like to have a more naive politician. So I will firstly tell about some naive calculation. That's already Martin told us today, but then I will mainly focus on the serious one. Okay, so the naive ones is the simple Elliott-Jaffet mechanism. I just want to say that Elliott-Jaffet were naive. It was basically naive that it was the first order perturbation theory. Yeah, so it was the first Born approximation, and what I am called not naive is everything beyond that. Yeah, just don't take the credit from Elliott and Jaffet. Okay, and I think Martin explained it nice that due to spin-orbit coupling, there is some mixture of spin-up and spin-down bands. So if I have a band structure such that the band structure is not spin-split, due to the spin-orbit coupling, which I can take as a small perturbation, I would see that there is some admixture. This is the B parameter Martin introduced us. Perturbatively, you are seeing it should be much smaller than the coefficient A. And then if you are now computing the spin flip rate as the overlap of the spin up and spin down state over some impurity potential, if you are applying those things, you are effectively seeing that those two things comes together, and you are just getting that this is the normal momentum relaxation rate for unperturbed, or let's say original electrons. So this is basically showing you that the inverse of the spin flip rate is proportional to the inverse of the momentum relaxation rate, and the constant is this B square, which we heard today morning. And the main thing is more scattering, more spin relaxation. It's like that. More stripes means more Adidas. So also in that case, it's like that. Okay, the second one is the diaconov of Perel, and it is if you are having the band structure which is spin split. So there is a break of the space inversion symmetry. So we are having a spin splitting here, and then we can effectively say that this spin splitting is like the effective magnetic field which depends on the momentum, and then the spin relaxation goes like that. So we are having electron which has a momentum, and if the momentum is conserved, the electron is precessing in this effective magnetic field. Suddenly there is a scattering event, the electron is changing its momentum, and then it starts to precess around different effective magnetic field. And again the scattering effects, etc., etc. So at the end, there is the effect Martin said, the motional narrowing. So in that case, more scattering means less spin relaxation. Okay, so this, let's say, was, I called it naive, let's say, very nice first order perturbation theory. And if you are taking this into account and you are computing typical values which you are having, so you are really getting that the spin relaxation in those cases due to those mechanisms is relatively very, very slow. Yeah? So you are getting the inverse rate, which is 10 to the power of 6 inverse second. And experiments, as I show you, is something around the 100 picoseconds. Okay, so what I have more? Okay, and then also the spin orbit, you should always see in those simple models that there is an anisotropy, spin relaxation, that spin parallel versus spin transverse. If you are injecting the spin like that or spin like that, you should see that there is some anisotropy which is close to 2, which comes very easily from those calculations. Okay, so let me tell you how to do it, let's say more, I am calling it advanced, but let's say correct term would be beyond the first order perturbation theory. So beyond the first order perturbation theory means that I am taking this seriously. So there is the orbital term, let's say also spin orbit term, in principle also magnetic term, but for simplicity don't consider it, or later I will do it. And what I am doing is I am really computing T matrix or self-energy fully. So I am not just taking the Born approximation, which would be the dead guy, but I am summing all of those diagrams, assuming this is this perturbation V. If you have the Green's function, which is, let's say, the most difficult theoretical task to compute, you can do it fully numerically, but then it takes too long. So one possibility is to analytically compute the Green's function and then just basically do that. It's just the matrix multiplication. Okay, and out of that, if you have the T matrix, you can compute transition rates, and transition rates are giving you the spin relaxation. So basically, this is what I am calling non-trivial or beyond. Okay, and you also see why you need it. Look here. So this is the spin relaxation rate in graphene, and this is the density of states, and this is the simple Born approximation. So you are seeing here the density of states, and the density of states in graphene is having this V shape. But if you are looking for the spin relaxation, it is exactly opposite like that. But the things which are staying here are just constant. Yeah, so by constant, you can never turn this curve to such curve. So the thing is telling you there should be something more, and the something more is that if you renormalize it. So if you are taking all the contribution together, you are getting this renormalization factor, and now what could happen? You can find some energy such that this guy is very close to 1, and that means the denominator is almost 0, so this thing will blow up, and this would be the thing which will cause you the blob, and then you can have the relaxation. So let's say this is some theoretical argument why resonance seems to be important. Okay, so basically this is how this resonant thing looks like. So I think this bridge feels much resonant, much relaxed in that case compared to that one. And this is how it means on the picture. So basically, this resonant thing means that the electron is coming and is locked inside of or close to the impurity for a certain amount of time. And then the impurity, since it is spin orbit active object, has enough time to flip the spin, and then the electron is leaving. So basically, this is behind the formula we just showed you with this large denominator. So this is, let's say, the pictorial or movie-like explanation of what is going on. Okay, and we did it. And for the hydrogen, for example, so we know the parameters as I show you. And we did it in two complementary ways. So I was calculating it analytically. As I explained you, this is the solid line. No broadening, nothing. This is just the data at 0 temperature. And then the guys in the Klaus-Richter group, they were computing it using the transport, using the quant. So they injected the spins, there was the impurity, and they were looking for that, and we are having a very nice matching. And you are seeing, if I would like to get the experimental value, which is 100 picosecond, I will need the impurity concentration, which is 0.1 to 1%, which is too much for the clean graphene. Yeah? I will never call things which has such amount of the hydrogen dirt as a clean graphene. Yeah, so basically you are seeing that spin orbit coupling or this Elliott-Yaffe mechanism needs large amount of the impurities to explain the experimental data. So we think that something different should be beyond that. And what is beyond that? That was the Yaro's idea, is that maybe this is a magnetic moment. Yeah?
So what is the dip that you have there?
This is because density of states, or if you are looking for this function in the denominator, it is changing a sign there, and this is due to such things.
So this is like a funnel
yes,
resonance?
It's like yes, it's like that.
And this is qualitatively different than what you would expect, than what you see experimentally. So that's.
If I will take this curve and do the thermal broadening and electron hole puddle broadening, you will see exactly the same curve. So this is, let's say, maybe the artifact of the drawing. So it is a little bit going down here, and it's like that.
Well, then it's not a funnel resonance.
It's not a funnel resonance because there is no the other channel which you need. You need the continuum states.
Yeah.
You need this. It's not like.
So it's an artifact.
It's an artifact of that. It's not. No, because in this energy, if you are doing this V potential, which you are downloading this orbital, you will see it's an Anderson-like impurity. Yeah, exactly. But this is the Anderson impurity, and it's not. Okay. So as I said, so Yaro's idea was that there are resonant impurities behind, but maybe magnetic moment we should look for. Okay? And that's basically just to give a credit to people who started with. So the first was Oleg Yaziev. I think he will be here next week. Also, Martin did nice calculations about that using the hydrogen and vacancy. And we are really seeing that if you are doing the DFT calculation and you don't constrain to non-magnetic solution, but you allow the magnetic solution, you will see that there is a splitting on the Fermi energy, and you are having the splitting between spin up and spin down electrons. Okay, there are, yeah?
Just for our curiosity, how do you allow for the magnetic solution? You have a little small magnetic field that induces the ferromagnetic.
I think the starting point, they are starting from some initial. I am not expert in DFT. I think they are starting with some non-magnetic trial wave function, and then it's iterating, or I don't know. Yeah, somehow. Marcin maybe can comment, or Paulo. Later. Okay, there are also some experimental evidences. So we heard the guy before me, he was talking about this universal conductance fluctuation. So there was measurements in the Joshua Falk group, and they were performing this in the case of the graphene, and they see that it scales anomaly going with the temperature going to 0. So basically one way how to consistently explain those data was that they assumed that there was some magnetic moments. There is also weak localization and anti-localization measurements, which show that also in the group in the Regensburg they did it. There was also the nice paper by Kawakami group when they put the hydrogen, then annihilated it, and before annihilation, and they compared the non-local signal, and they see this peculiar dip in the Hanle curve or in the non-local measurements, and basically they were only able to explain if they assumed that there was some random fluctuating magnetic field which can do things like that, or famous Madrid experiment when they put the hydrogen and they see some splitting and they interpret it as a splitting or maybe Kondo, I don't know. So there are some experimental evidences as well. Okay, and this is in which case? Very low, so here 15 Kelvin. Here I think it was maybe helium cryostat, so I don't know the details. Everything is very low. Okay, so this formula you already see. However, in this case, we are having, instead of spin-orbit coupling here, this magnetic moment. So I am having this, do I have it? No. I will show you. So this is the first thing which I was showing you. This is this resonance, which I was showing you the video before or the animation before. So the electron is spending a certain time around the impurity. And if you ask yourself, how I will compute this time? So you can compute it. So you are having a density of state. This density of state has some bulb. And the width or half width of this bulb, inverse of that is telling you what is effectively the trapping time around the impurity. Yeah? So you can get it. Okay. And okay, the people are saying, or at least in the Zeldo group, there is a very nice experiment, and they are seeing that they are able to see resonances. So they are having some dirts on the edges, but they are also seeing things inside of that. So seems that maybe resonances. This is the photo of not black hole, but of the resonance. And this is our model. So our model is everything what was before, but now we are also assuming that there is a magnetic moment which is located on the impurity side. And there is another effective time scale, which is this Larmor precession time, which is basically energy splitting divided by h bar, or opposite h bar divided by this energy, is roughly giving you the Larmor precession time. How long does it take for the electron, if electron is here, to precess around the induced magnetic moment on the impurity? And everything is just a matter of those times. If the Larmor time is shorter than the trapping time, then the impurity really acts as a hotspot, or it acts really as a scatterer, because there is enough time to spin the flip. And if it's opposite, then it will not work. And this is the results. So this is the results of that model which I am showing you. So the first thing is that there is a very weak temperature dependence for this moment, and this is consistent with experiment. So experiment showed that the spin relaxation in graphene is weakly temperature dependent. And this also we are seeing that this resonance scattering mechanism on magnetic impurities is really weakly temperature dependent. So this is the, let's say, fit or adjustment to the experimental data. So what we were just adjusting was the concentration of the resonant magnetic impurities. So our impurity needs two things, to be resonant and to be magnetic. And we just need less than part of the million to explain that. And the same thing was done for the bilayer graphene. And in the bilayer graphene, that's exactly what I was saying you before. So here you are seeing this hype. However, in the bilayer graphene, you are seeing a dip. And this comes from the exchange. So in both cases, if you are just looking for the orbital perturbation, then you are having this resonance. But if you are applying the exchange interaction, then you are getting singlet and triplet splitting. And now depending how far it is from zero and what is the broadening due to electron hole puddles, you either completely wash it out, as is the case in the graphene, but there can still be the traces in the case of the bilayer graphene because the density of state is the different one, so the dynamical broadening is different, and this is the artifacts of that. So this is basically explaining those two things. So here we are really having a valley in the bilayer graphene, while in the single layer graphene we are having just one hype. Okay, so we made few particular predictions. Okay, there were some other studies confirming or basically showing that the magnetic moments are really detrimental for that. And then we made few predictions, and those predictions were nicely confirmed by another paper by Roland Kawakami. So we were predicting that in bilayer graphene, you still have more degrees of freedom because you are having 4 atoms in the unit cell, and bilayer graphene slightly differently responds to the hydrogenation. So we were predicting that there should be 2 peaks, and basically they are really seeing them in the experiment. So we were able to explain those experimental data just by that. But I don't want to go here deeply into the details. Just want to tell you that there was some continuation of that, And it seems we are still consistent with the findings by experimentalists. Okay, here I still have some time. Yeah.
So that peak that you have, it's maybe one back, maybe one more. The theory. Yeah, one more. Yeah, there. So what controls where this peak happens? Because it's asymmetric, right?
Yes,
Can you change the sign of
yes,
the
you
Curie
sure.
potential?
This is dictated by the on-site energy of the adatom. So basically, if the adatom has a opposite energy compared to the graphene, so let's say it's negative, then it will be on the opposite side. So the position of the peak is controlled by the epsilon, and the width is, there is a complicated function which tells you how it is related with the omega. So the width is controlled by omega. Okay. Okay, there are still open questions. One thing is what superconductivity will do, and this I want to talk next week. And I will show you that there are some interesting results about that superconductivity can still give you another knob which you can play with, and there are nice and intuitively understandable results about that. Okay, so let me go to the last thing. So you remember I started with slide like that, where I was saying you something about the functionalization by adatoms, and now it's a time, but I will try to be fast to tell you that what happens if you will put the graphene on the substrate, and this is also the propaganda for our friends. You can look for the papers about the proximity, but there is not only spin-orbit coupling proximity, there is a proximity by many other things. So it's the paper by Igor Žutić, which appears in materials today. Okay, so we started, and I think in Jaro's group they're still continuing to do DFT about that. So you put a graphene on top of TMDC, let's say moly or tungsten diselenide or sulfide, etc., etc. And the basic picture is like that. And there are also some relevant references who started or who did something independently of that. And let me come to the point. So what we are expecting. So you are putting a graphene on the TMD. And TMD is composed, let's say, there are these dichalcogenates, either selenide, sulfide, even telluride, or some other guys. And as a transition metal, we start in moly and tungsten, but also you can go to rhenium or other things. And the main feature of that is that this is a typical van der Waals difference. So if you put it, relax it, and look how it looks, you see that the difference is typical van der Waals difference. 3-5 angstroms. I think 3 is more closer. Okay, so what we are expecting is that we are breeding two materials in a sense. There is a graphene which has a perfect high mobility, very weak spin-orbit coupling, beautiful relativistic Dirac cones, let's say. And now we are having a wideband semiconductor which is spin active because there is a K and K prime valley which are having opposite chiralities. So there is a belief that if the distance is not too much, they will not talk too much, and what we can have both things. So we can have a gap from the TMD, and this gap is rich for the spin-orbit coupling physics, and then we'll have these Dirac cones, and we believe that some of the spin-orbit coupling will affect these Dirac cones. Let's say this is the hopes we can get. And this is really what happens. So this is the DFT calculation by Martin. I don't know for which one. I think for all those three, moly, tungsten, selenide, sulfide. And it's exactly as you would naively expect. So there is a gap. And if you are looking for the orbital decomposition of the states, you really see that this is the moly guys. If you are looking inside, you are seeing the Dirac cone. And if you look, this is a PZ electrons. But if you zoom in, then you start to see the spin orbit things. And the colors tells you what is the spin expectation value of spin up or spin down. And here in these three cases, it's boring. It's some quadratic. But if you are looking for the tungsten diselenide, you are seeing that there is the inversion. So this band is going up, and this band is going down. Okay, so this is probably because tungsten is much heavier. Selen is also much heavier. So there is some competition between lightness and the spin orbit and things like that. So that was, let's say, the surprise. And we were thinking that we discovered some topological material. So we were very excited about that. Later we show that it's not topological, but still it's interesting. Okay, so the model which we were doing is, so we wanted to describe all such things which can happen. And the model is provided here. And the things, and I will show you on the next slide, which controls whether it is inverted or not, is described by those two parameters. The delta is the staggered potential, and lambda intrinsic is some combination of two spin-orbit couplings. So let me see whether I have it on the next slide. Yes, it's like that. So this is the top view, how the things look like. And you are seeing they are not perfectly matching. But if you drink enough cachaça, you see that one sublattice is more affected by tungsten, and another is more by moly or things like that, or transition metal. And then you can somehow see that, okay, on a very grain-looking view from distance, you can say that one sublattice feels different effective potential than the other one. And basically, this is this hopping delta, which I will show you. This is the staggered term. So effectively, we are breaking the sublattice equivalence. And the other thing which is interesting is that in the K and K prime valley, there is this inversion. I am apologizing for the quality of the figure. It's from the Igor's paper. So you are seeing that the spin ordering in K and K prime on the moly is different, and this somehow transferred to the fact that the intrinsic spin-orbit coupling, or spin-orbit coupling which we are calling intrinsic, you see the Hamiltonian, is different from the spin-orbit coupling on the sublattice B, and they are differing in the sign. So that's what I wanted to say, show you that. So on one sublattice is like that, on another is like that, but what matters is the combination of them, either plus or minus sign. And if they are on the same sign, then you will have this picture, and okay, I will go to that slowly. So okay, this is the let's say output of the model and output of the fitting to the DFT data. And now let's go and see what this Hamiltonian is doing. So those two terms are nothing else as the graphene thing. So basically, this term will give linear dispersion, but since you are having the spin-orbit coupling, this intrinsic spin-orbit coupling, I was talking, Barchin was talking, you are seeing that this is this 24 micro electron volt gap. But now, if you are taking, what happened? If you are now taking the staggered potential and this another spin-orbit coupling, two things can happen. In the staggered potential is larger, the picture will lose like that. The colors denote the spin. However, if the lambda intrinsic is larger, then you will see that this band is going down and this up, so you are seeing this figure. So there is this inversion, so which is going down. And then what is doing Rajba is doing that spin is not anymore good quantum number, so you are seeing the opening of those things. So this is, let's say, on the level of the model we understand. In the level on the atomism, how and this, how it's opposite and blah, blah, this we don't fully understand. Okay, so then we played with the nanoribbon. So Toby was comparing two scenarios, if the two lambdas are having the equal sign or the two lambdas are having the opposite sign. And you see that if you take the Haldane model, the picture is completely different. So this is the standard Haldane model when you are having these David star hoppings, which are basically all in the same direction. But in the case which is also group theoretically allowed, you can have the hoppings which are basically opposite on those two triangles. And in that case, the band structure will lose like that. So this was for one spin species, and if you combine both species, you are getting these things. So this is the standard Kane and Mealy edge states, but in our case, you are seeing that there are some edge states which are lying inside, but there are also some valley dependent states. And what comes as a surprise is that, okay, because of that, so just want to tell you, so this is the direction in which you are changing the Kane and Mealy things. So you are going from topological to trivial to topological. This is the direction in which we are going because our lambdas are opposite. And if you compute Z2 invariant, it's trivial. But, there is a one but, you can gap out those states by finite size effect. So if you're taking the nanoribbon, which is a finite, you can gap out those states. So at the end, what will happen? You will have just edge states. And this is exactly the situation will happen. So with the nanoribbon, and this is for realistic nanoribbons, you really don't need a small. This is the realistic, let's say, 100 nanometers or even more. For those parameters which we have, it still is enough to gap out those valley states, and what will survive are only those states which are calling a pseudo-helical. And there is a big difference. Our pseudo-helical states, if you are looking, the same spin is going in the same direction. However, in the Kane and Mealy, it's opposite. Yeah? So spin up is going here on that edge, and on that edge, it's going opposite. Yeah? So there is a difference of the spin texture or spin the dynamics of that. Okay. So are they true edge states? And the answer is that they are not true edge states, but still you are able to have such transport which spin is going, and then there is some complete spin flip tunneling on the edges, and this is the difference between our pseudo-helical states and that. So basically by Z2 invariants, they are clearly not topological. because if you're making the system really 2D, very large, then basically those valley states you cannot get out. So basically this will spoil all the picture. So basically you see, yeah, topological protection is here. And basically that's all. So thanks for your attention.
Questions?
Dennis, your PIA term that you mentioned in the beginning, if I understood correctly, it only exists if you have the adatom in the...
No.
No.
No. If you reduce the group from D6H, which is the full plain graphene point group, to some subgroups, then you see that in 2 cases it can appear also in the bulk.
But if you don't reduce the group,
Then not.
then this is different than what Marcin showed. We
No,
have plain graphene.
No, Marcin showed the PIA, which was exactly this term.
Okay.
I was referee of the Bjorn paper. Bjorn knows it, and also now Evelina. No, I'm kidding.
Okay. Then another comment.
Yeah.
You could have added a Brazilian politician to your joke.
Yes, I could.
Maybe
But
for next week.
Yes,
Maybe
but
for
if
next week.
if I would be outside of Brazil, I will do it.
Any further questions? I have a question. So in your helical model, then wouldn't this mean that the previous one, wouldn't this mean that you break time reversal symmetry? in
No,
this?
it's not. It doesn't bring it's not, because spin up, if you are then changing the spin up to spin down and direction, you will basically see that it's going opposite. It's not.
So in the spirit of the more colloquial presentation, on the first part with the adatoms, right? You only looked at non-magnetic adatoms, right?
Not
What
magnetic,
happens
yes.
if you have a
Yes.
magnetic?
Then we know, because there were other studies, the point is that they are not going on top position, they are going more to the hollow one. And the other thing is that there is still few debated issue whether it's a really chemisorption or it's more physisorption. Because this bonding was not too strong. And then there are some other models which basically are specially developed for heavy atoms which are having very strong intraatomic, like thallium or I don't know, osmium or something like that. So there is Jason Alisa, Marcel Franz, they are having paper about that. But we were not focusing on that, yeah.
So it's also related to Alex's question. Of course, when you complete the loop, if you think of this system as you just showed before, right? There. So then here, of course, it's the quantum spin or anomalous if you're just showing one, but then you have two. And there, right there on top, you have a twist because you have some kind of spin orbit that,
Yes, exactly.
Now, suppose you have a finite system, you connect that to a lead, up there and down there, source and drain. Then how can, do you still believe that this would hold?
I believe, yeah.
So where would the twist?
If the leads will be here.
Yeah, so now I make contact there with the
here.
metal. Yeah, either there or up there. So
So our states are propagating, that I maybe should stress, only on the zigzag edge, not on the armchair. On the armchair, you see that spin quantum number is not good, and you start to see that there is a spin turning. And
but that
spin
will depend on the detail of the interface, because I could imagine that if I have strong, tunneling, tunnel coupling between the, the graphene and the lead, that I could destroy the spin orbit interaction, and then the whole picture would not be valid in this sense, right?
In a sense, yes.
I guess here, for the topological case, this is protected in a different way, even if you...
Yeah, I agree. Yeah,
so in a way, actually, I know this result from Jaros many years ago, and I would say this is similar to this geometric protection that I mentioned in the quantum dot, where you...
I agree. I think it's a geometrical...
it's actually a nice... Another example of that, the fact that you can have edge states that are not topologically.
Yeah, I think that Inanch, when he saw those results, he exactly used the term geometry-induced topological transition, that if you make the system not so big, you can gap out some states and only few guys will persist, and those because of time reversal symmetry, are blocked to backscattering.
Yeah.
Yeah, but exactly as you said, yeah, that's the same.
Thank
I
you.
would say.
Any further questions?
Actually, this is not a question, this is a comment, because when you were telling us about the spin relaxation times in graphene, so you mentioned that this is like 10 or 100 picoseconds, and what would lead to think like that we could think that graphene is not really good for spin transfer channels. But recently, I think it's paper from 2014, they found that because those experiments you showed, I think it was pristine graphene and electrodes on the top of graphene, but if you encapsulate it in HBN, in boron nitride, so it stabilizes the flexural distortions and also the penetration from adatoms, and they measure the relaxation times up to 10 nanoseconds. So
up to 10, I know one, but
no,
maybe
they say 6, but in the paper is some kind.
Yeah, I know that Bernd Beschoten group in the Aachen, they are reporting very strong, very long spin relaxation, but it's very clean graphene and encapsulated.
Yes.
In that case, it's clearly you are basically blocking the adatoms to come to the game, or you are also healing those impurity. Because I showed the hydrogen, but the same effect would be if you will have the vacancy. Vacancy also known to be very strong resonant impurity, which brings the magnetic moment. So you can believe that if you are encapsulated, thanks Martin, exactly, you can heal that in a sense, and you are blocking a channel for spin relaxation, which is also somehow along our lines.
Yes.
Yeah.
There is a hope for graphene in spintronics. That's what I wanted to say. So.
Yes, I showed those two propaganda papers, and they also hope that.
Won't be out of the job. Any further questions? If not, let's thank Denis again and all the speakers of this session. Of the week as well. So yes, so as one of the